So, we will continue our discussion on the construction of Bode plot. In the last class, we discussed the construction of Bode plot with taking 3 examples. Fine. So, today we will discuss the construction of Bode plot for a first order system. So, the transfer function of a first order system is written as k divided by tau s plus 1. This is the transfer function of a first order system. Now, we obtained the expressions for amplitude ratio and phi in the previous class as amplitude ratio equals k divided by root over of 1 plus tau square omega square, and we obtained the expression for phase angle as phi equals tan inverse minus tau omega. Now, we will take the logarithm of this amplitude ratio expression in both sides. Then we can write as amplitude ratio by k, log amplitude ratio by k equals minus half log 1 plus tau square omega square phi. So, this is the magnitude ratio basically. Next, we will consider the asymptotic considerations. Before making the plot, we need to discuss the asymptotic considerations. First, we will consider the amplitude ratio. First, we will discuss the amplitude ratio. Then, we will discuss the phase angle. Fine. Now, if we consider tau omega tends to 0, if we consider tau omega tends to 0, then amplitude ratio by k tends to 1. Here the amplitude ratio is multiplied with 1 by k, that means this is scaled amplitude ratio, and here we are considering scaled omega, I mean tau omega we are considering. Now, if we consider tau omega tends to 0, then amplitude ratio by k tends to 1. So, we can write that log amplitude ratio by k tends to log 1. Fine. So, at the very low frequencies, the log plot of magnitude ratio versus tau omega tends to the horizontal line. At very low frequencies, the log plot of magnitude ratio versus tau omega tends to a horizontal line represented by magnitude ratio equals amplitude ratio by k equals 1. Fine. Since this situation arises at low frequencies, this line is called low frequency asymptote. Since this situation arises at low frequencies, this line is called low frequency asymptote. Fine. Now, if we produce the plot considering this equation, I mean this line, then what we obtain? So, here we are considering tau omega, and here magnitude ratio. This is a log plot. So, we are using log graph paper. This is 10 to the power minus 2, 10 to the power minus 1, 1, 10, and this is suppose 10 to the power plus 2. And here we are considering 10 to the power minus 2, 10 to the power minus 1, then suppose this is 1. Fine. Now, we obtained this form log amplitude ratio by k approximately equal to log 1 when you consider low frequencies. That means, it is clearly a horizontal line. Fine. So, this is the low frequency asymptote. This is low frequency asymptote. Fine. Now, under asymptotic consideration, next we will consider tau omega tends to infinity. In the next we will consider tau omega tends to infinity. As tau omega tends to infinity, then we can write log amplitude ratio by k tends to minus log tau omega. When tau omega is much greater than 1, we can neglect this one term. I mean, this is the general form. When tau omega tends to infinity, we can neglect this 1. That means, this right hand side becomes minus log tau omega. Agree? So, when tau omega tends to infinity, we can write log amplitude ratio by k tends to minus log tau omega. So, the log plot of magnitude ratio versus tau omega tends to the line represented by log magnitude ratio approximately equal to minus log tau omega. In the log plot of magnitude ratio versus tau omega, we need to consider this equation, log magnitude ratio approximately equals to minus log tau omega. This is nothing but a straight line with slope minus 1. This is a straight line with slope minus 1, and this situation arises at high frequencies. Therefore, this straight line is called as high frequency asymptote. Since this situation arises at high frequencies, this straight line is called as high frequency asymptote. Fine. So, using we will next consider this equation in the Bode plot. So, it is basically a straight line with slope minus 1. So, this is representing the high frequency asymptote. This is representing high frequency asymptote. It has slope of minus 1. Fine. In the next step, we need to determine the point of intersection. In the third step, we need to determine the point at which the two asymptotes intersect. When we consider tau omega tends to 0, we got log amplitude ratio by k is nearly equal to 1. This we considered low frequency asymptote. When we consider tau omega tends to infinity, we got log 1, no. So, when we consider tau omega tends to infinity, we got log amplitude ratio by k, which is approximately equal to minus log tau omega. Fine. Now, if we equate these two equations, equating these two equations, we obtain tau omega equals 1. Agree? Equating these two equations, this one and this one, we obtain tau omega equals 1. That means they intersect at tau omega equals 1. Now, in this situation, we usually use one suffix for this omega, that is n. at this situation we use the suffix n for omega, that means we can write tau omega n equals 1. The value of omega at which these two asymptotes intersect, that is called natural frequency. So, here omega n is the natural frequency. And most popularly it is called as corner frequency. It is also called as break frequency. Fine. Now, can we determine the exact values of the magnitude ratio at this corner frequency? What is the exact value of magnitude ratio at this corner frequency? We have the expression of magnitude ratio, that is magnitude ratio equals 1 divided by root over of 1 plus tau square omega square. Fine. So, this is the exact value of magnitude ratio at corner frequency. Accordingly, we need to construct the Bode diagrams. I mean, this magnitude ratio versus tau omega plot should looks like this. Like this. And the corresponding tau omega is 1 here. This is the corresponding natural frequency in this first plot. So, this is the asymptotic considerations in terms of amplitude ratio, and we obtained this plot. Similarly, we need to consider the asymptotic consideration in terms of phase angle. So, next we will consider the phase angle. As tau omega tends to 0, phi tends to what? 0. Fine. In the second, as tau omega tends to infinity, how much is phi? Minus 90. That means phi tends to minus 90. So, phi never be less than minus 90. Fine. It clearly indicates that phi never be less than minus 90. And in the third situation, we will consider the corner frequency. At the corner frequency, that means tau omega equals 1. How much is phi? Phi is minus 45 minus tan inverse 1. So, this is minus 45. So, these are the asymptotic considerations in terms of phase angle. Now, we will draw the phi versus log tau omega plot. This is the semi-log graph paper, and this is 1, which corresponds to the corner frequency 10 to the power minus 2, 10 to the power minus 1, this is 10 to the power plus 1 and 10 to the power plus 2. This is suppose minus 100 degree, minus 90 degree, this is say minus 45 degree, this is say 0 degree. At low frequencies, the tau omega, the phi is 0. Fine. So, it is somewhat like this. At low frequencies, phi is 0, and when tau omega tends to infinity, we obtain phi minus 90, and when tau omega equals 1, we obtained minus 45. Agree? At low frequencies, this phi is near to 0, and as tau omega tends to infinity, this is minus 90, and at corner frequency, this is minus 45. So, this is the Bode plot for a first order system. This is the Bode plot of a first order system. In the next, we will discuss the construction of Bode plot for a second order system. In the next, we will discuss the Bode plot of a second order system. So, the transfer function of a second order system we considered earlier taking this form, I mean Gs equals k divided by tau square a square plus 2 zeta tau s plus 1. And in the last class, we derived the expressions for amplitude ratio and phi. So, there amplitude ratio divided by k equals 1 divided by root over of 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. This expression we derived earlier. Similarly, the expression of phi is written as tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square. Fine. These two expressions we derived earlier. Now, we will discuss the asymptotic considerations in terms of first amplitude ratio followed by phase angle. asymptotic considerations. First we will consider amplitude ratio. As tau omega tends to 0, amplitude ratio by k tends to 1, and log amplitude ratio by k tends to log 1. Fine. As tau omega tends to 0, we obtain amplitude ratio by k tends to 1, and accordingly log amplitude ratio by k tends to log 1. Now, it is clear that the low frequency asymptote is a horizontal line. It clearly says that this is a horizontal line. Next, you will consider tau omega tends to infinity. So, as tau omega tends to infinity, log amplitude ratio by k tends to minus half log tau to the power 4 omega to the power 4. Here we neglect all lower order terms. Fine. So, this is equal to basically minus 2 log tau omega. As we consider tau omega tends to infinity, we obtain log amplitude ratio by k tends to minus half log tau to the power 4 omega to the power 4. Here all low order terms have been neglected. So, it is then becomes minus 2 log tau omega. So, this is a straight line with slope minus 2. So, this is a straight line with slope minus 2. So, the low frequency asymptote is a horizontal line and the high frequency asymptote is a straight line with slope minus 2. For the first order system, we obtained horizontal line as low frequency asymptote, but high frequency asymptote is a straight line with slope minus 1, and for second order system the slope is minus 2. Now we can produce the plot of magnitude ratio versus tau omega. Before that, we need to determine the point of intersection. Fine. So, this is a third step. So, we got basically log amplitude ratio by k, which is approximately equal to log 1. this equation we obtain at low frequencies, and for high frequencies we obtain minus 2 log tau omega. So, equating these two equations we obtain again tau omega equals 1. Again we obtain tau omega equals 1, but here we cannot determine the exact values of magnitude ratio, because that is also function of zeta. Here the exact value at corner frequency we can obtain only knowing the value of zeta. So, here the magnitude ratio can be obtained by knowing the value of zeta, and this should be reflected in the Bode plot. Fine. Next we will construct the Bode plot, and first we consider magnitude ratio versus tau omega. Say this is 0.1, then 1, and this is 10. 0.01 the starting value of magnitude ratio, next one is 1, and this is a 100. So, at low frequencies we obtained a horizontal line, fine, and at high frequencies we obtained a straight line with slope minus 2. It was mentioned that the magnitude ratio at the point of intersection depends on the value of zeta. So, accordingly we will consider 3 different cases varying the zeta values. This type of response we obtain if zeta is say 0.6, which is quite less. This one we obtain when zeta is say 0.9, and this plot we obtain when zeta is 1. Fine. Considering 3 different values of zeta, we obtained 3 different plots as magnitude ratio versus tau omega. So, these are the 3 plots. This top one corresponds to zeta equals 0.6, next one corresponds to zeta equals 0.9, and this bottommost one corresponds to zeta equals 1. Next we will discuss the asymptotic considerations in terms of phase angle. Next we will discuss the asymptotic consideration in terms of phase angle. when tau omega tends to 0, we can write phi equals tan inverse minus 2 zeta tau omega. Can we write this? This we can write when tau omega becomes much less than unity. When tau omega much less than unity. Fine. Now, if we consider tau omega tends to 0, now if we consider tau omega tends to 0, this phi approaches 0. Agree? If tau omega is much less than 1, we can write the phi expression like this, tan inverse minus 2 zeta tau omega. Now, if we consider tau omega tends to 0, the phi approaches 0. Secondly, if we consider tau omega tends to infinity. So, in this case we can write the phi expression as tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square. This is the original expression. We can write this as tan inverse minus 2 zeta divided by 1 by tau omega minus tau omega. Agree? So, this is equal to tan inverse 2 zeta by tau omega when we consider tau omega tends to infinity. Agree? So, this one we can write in this form considering tau omega tends to infinity. So, then phi tends to tan inverse 2 zeta by tau omega, which is equal to tan inverse 0. Agree? This expression we got. Now, we are considering tau omega tends to infinity. So, we can write tan inverse 0 and this is equal to minus 180 degree. This is considered as minus 180. Fine. In the third case, we will consider tau omega equals 1, I mean the point of intersection. Tau omega equals 1. Now, in this case, regardless the value of zeta, phi becomes tan inverse minus infinity, which is minus 90. Tau omega equals 1 corresponds to the corner frequency, and regardless of the value of zeta, we obtain phi equals tan inverse minus infinity. That means this is minus 90. Now, you see, initially we consider tau omega tends to 0 and this is tau omega equals 1. So, this is the lowest one, this is the intermediate one and this is the highest one. Fine. Here the phi value is maximum, this is intermediate and this is minimum. So, there is a trend in Bode plot. Fine. Now we will try to produce the plot between phi versus tau omega. And this is phi. .1, this is indicating 1 and this is 10. This is suppose minus 200 degree, minus 180 degree, minus 90 degree, 0 degree. This plot also considers the different values of zeta. This is one plot. This is the second plot. This is the third plot. This top one we obtain for zeta 0.6. Second one we obtain, I mean intermediate one we obtain considering zeta 0.9, and this one we obtained considering zeta equals 1. Fine. So, this is the Bode plot of a second order system. The top one is plotted in using log graph paper, and the bottom one is obtained considering semi-log graph paper. Fine. In the last example, we will consider a feedback control system, a feedback controller, and we will construct the Bode plot. So, next we wish to discuss the construction of Bode plot for a P only controller. The transfer function of a P only controller is Kc, I mean Gc equals Kc. So, we can write amplitude ratio equals Kc, and the phase angle we can write as phi equals 0. So, both are independent of omega. So, it is easy to develop the Bode plot. This is indicating omega and this is indicating amplitude ratio. Since Kc is independent of omega, this should be a straight line. Agree? In the bottom plot, we consider phi versus omega. and phi remains 0 all the times. I mean that is also a horizontal line having phi 0 degree. So, this is the Bode plot of a P only controller. Next is the PI controller. The PI controller has the transfer function and it can be written as Gc equals Kc 1 plus 1 divided by tau is. Replacing S by j omega, we can write the frequency response transfer function as Kc multiplied by 1 plus 1 divided by j tau I omega. We can write this as Kc 1 minus j tau I omega. Agree? So, from this Cartesian form it is straightforward to determine the expressions for amplitude ratio and phi. So, amplitude ratio we obtain as Kc root over of 1 square plus 1 divided by tau I square omega square. Fine. Similarly, we can write the expression for phi. Phi equals tan inverse minus 1 divided by tau I omega. This is the expression for phi. Now, we can write this expression of amplitude ratio by taking logarithm as log amplitude ratio by Kc equals half log 1 plus 1 divided by tau I omega whole square. If we take the logarithm of this expression, we can write log amplitude ratio by Kc equals half log 1 plus 1 divided by tau I square omega square. Fine. In the next we consider the asymptotic considerations. First we consider the amplitude ratio. As omega tends to 0, one by tau I omega whole square becomes much higher than 1. Agree? So, we can write as log amplitude ratio by Kc tends to half log 1 by tau I square omega square, which is equal to minus log tau I omega. Agree? If we consider omega tends to 0, we can say that 1 by tau I square omega square is much higher than 1. Then this expression yields this. So, the low frequency asymptote is a straight line. So, this is a straight line with slope -1, fine. So, what will be phi then if we consider omega tends to 0, phi becomes tan inverse minus infinity, agree? Which is equal to minus 90 degree. It is very straightforward because we have this expression, we are just considering omega tends to 0. In the next step, we will consider omega tends to infinity. Then 1 by tau I square omega square approaches 0. Accordingly, we can write log amplitude ratio by Kc tends to log 1. So, at high frequency, the high frequency asymptote is a horizontal line. High frequency asymptote is a horizontal line. And how much is phi if omega tends to infinity? Phi becomes 0 degree. Next one is the determination of corner frequency. We obtain the corner frequency when tau I omega n equals 1.0. Fine. Accordingly, phi becomes minus tan inverse 1, which yields minus 45 degree. And amplitude ratio by Kc becomes root 2, which is 1.414. Fine. So, these are the asymptotic considerations, and next we will make the plot. Amplitude ratio by Kc and next one is phi versus tau I omega. So, when omega tends to 0, we obtained a straight line with minus 1. Somewhat like this, and this is indicating the corner frequency. And when omega tends to infinity, this is a straight line like this. Fine. So, we get this type of Bode plot. Similarly, here we obtained minus 90, we obtain like this plot for phi versus tau I omega. Yeah, this should be like this, this is 45. Okay, I am redrawing it. Tau I omega, this is suppose 1, this is minus 90 degree. So, this is minus 45 and this is 0 degree. So, it will go like this, fine. So, this is indicating the corner frequency at which phi is minus 45, and at low frequencies this is minus 90, and high frequency, at high frequencies this is 0. So, you just do not consider this one, fine. So, this is the Bode plot of a PI controller. Bode plot of a PI controller. Okay, thank you.